Boom, boom, boom. Okay. Anybody still want one of these? Me? Straight away. I have to remember, I've got a mic on. Hold on. I'm going to move that further down. You can listen to my digestion. Yes? Somebody else that I've missed on the way past? Did I miss anybody? I'll bring more. I've still got more in my office. Yay, you finally made it. Any more? Somebody else missing? Very good. Okay. All right, morning everybody. The last roundup, as they say. So let's commence. You're all very obedient this morning, talking away. Focus, 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 hocus pocus, focus. Right. So the last roundup. Last chapter, 2 lectures. One this afternoon, 2 o'clock. Tutorials upstairs in Reynolds D9, D1, 2, just to remember. Thank you to the diehards last week. 16 or 20 of them in total, who could walk up the staircase. Not that I mind. Right, so catalyst materials. So this is a little bit more of a slide presentation rather than having notes with it. Now you have in the handout, in the handbook, at the back, there is an article written by a chap called John Dwyer, who now I think is 84. He's my ex-supervisor from a long, long time ago. And it's an interesting read. It might be high-end, so there might be stuff you don't get, but it's useful. Those of you doing design projects and have already come across nickel Sapo 34 or Sapo 34s and zeolites and so on, fine. Those of you who did the exercise, which is all of you on the coursework, you'll have seen zeolites in pretty much all of the things that you saw. So this is a bit of grounding in that. So if you've still got your papers from the exercise for the coursework, which quite a few of you still have because you didn't leave them behind. Also, I put the references up on Blackboard, I think. I might not have done all of them, but I'll have a double check just to check if I put them there, and then you can have a go at finding them through the library and eScholar. But at this stage of the term, or the semester, I think you're very much aware of design projects. You're focused in on your deadlines for that, and therefore I don't want to overly stress and strain you. So, zeolites. Catalytic materials full stop. You'll find out there's more than just zeolites. I put a different zeolite structure today, and I'll bring 3 this afternoon so you can have a look at them. So this lecture is all about awareness of catalysts, catalyst support. You've got the idea from previous lectures that a catalyst provides active sites. Those are predominantly homogeneously spread throughout a particular structure, or they're on the outside because there isn't much surface area. You've got that idea. You know that the steam reforming one, which was very chunky, was a nickel on alumina catalyst, and the shift catalysts were pellets, size of your little fingers. I brought them with you, but just to remind you, they're these little bottles, and that's the particularly chunky one. So, think about that. Think about where they come from. You've had an introduction to zeolites, but those in industry, so those who aren't working in oil and gas, won't have a clue about zeolites. So this is by way of helping them more than it's helping you, because I think you will have a better awareness of zeolites. I also want to show you their refinery context, which is large. So now is it timed? Yes, there we go. So carbon is often used as a support in hydrogenations. So carbon can be a support. You had a tutorial problem that listed carbon as a support and asked you to pick its selectivity, was it good at activity, did it have a high surface area, and so on. Silica alumina SiAlO structure are zeolite structures. Iron is a hematite structure, which is used for the methanol synthesis catalyst. Then you've got copper and chromium that are in that shift catalyst with the iron. Then you've got cobalt and nickel moly catalysts. So molybdenum should come up in a minute if it hasn't already. There you go. So molybdenum and tungsten and nickel and cobalt are commonly used for desulfurization. Palladium and silver are also used as hydrogenation and dehydrogenation catalysts, along with platinum and gold. Rhenium and ruthenium and other elements are also used as catalysts, and titanium is an oxidation catalyst. Those of you familiar with Japanese toilets have self-cleaning seats because they've got a layer of titanium dioxide on it. I knew you always wanted to know that, but there you go. So antimony there is also used as a catalyst. In what? In the PET bottle that Madam has just got there in front of us. So PET catalysts have got antimony in it. It's still in the bottle. It's also one of the most deadliest things known to human beings. Now, while we weren't looking, it also brought up the lanthanide series in cerium and lanthanum down at the bottom. They're additives to make structures more stable that go within the catalysts and the supports. So, that's the periodic table, the home of the chemist. But the most important thing of that is you can see that that's why chemists are involved in making catalysts for you, because you're really covering the transition metals at the top, the lanthanides down at the bottom, and you're talking about the basic raw materials of stuff: carbon, silicon, oxygen, aluminium, and titanium dioxide. So predominantly oxide catalysts forming different structures, but pretty much a good covering of the periodic table. And a hell of a range of reactions. So, common supports. You've got activated alumina. So, what is alumina? It's just Al2O3 to you, but it also forms polymeric structures. It's also a white powder. You can make it so that... I didn't want it to do that. What's it doing? It's going backwards, is it? Silly thing. Let's just get the whole slide up. Okay, we're not going to get the whole slide up. Sorry about that, guys. All of you now feel ill. Please take a moment. I don't know what's going on with this presentation since last week. It completely messed up my pen drive. All right, so activated alumina, most common, varied acidity. Good, it fades out. Hopefully now it brings up the one in the middle, which is carbon. So activated carbon, prepared from natural sources. There are different types of carbon. Carbon is microporous and mesoporous, and you can prevent. You're pretty familiar with it on a Barbie, but one of the coconuts that's a really interesting source of carbon is coconut. Coconuts float around the world, and they basically have a very microporous structures because you never end up with... I'm going to do it again. So it comes up again. For some reason, it's not phasing in the way it should. I have no idea why. Forgive me. It's in front of you, hopefully, though. So carbon itself is an interesting material because it's low temperature. It is very high surface area, and you can react it to produce all sorts of wonderful hydrogenations. The organic chemists love it. So that tells you a little bit about it. It's natural, so it's varied if it's natural. Things that are natural are not the same over and over again, so we don't manufacture it. We use natural sources, and you use it quite often for absorbance. And the last one on there is zeolites, which have we got the crown jewels of catalysis. Please do not write that in the examination. It does not win favour with the marker when you write crown jewels. It's just me saying they're the crown jewels. If you write it in the exam paper, I know you've been paying attention, but they're crystalline aluminosilicates. That means that they form a structure. That means you can see the structure deep into the structure. It means when you do an X-ray pattern of it, there are lots of atoms that you can bounce back on. And it's used in shape selective cracking. So, key things to notice here are the properties, and common alumina oxides are at the top, but then at the bottom is a list of the different types of catalysts and the different kinds of supports. Now, don't be confused, because the BET surface area is, as we've said before, it's how big a surface area we've got. It's large. But there are three kind of major supports and catalysts. Activated carbon is not a catalyst in its own right. It's a support. Zeolites are catalysts in their own right, but could also be a support. And activated alumina is a catalyst that could also be a support, but is predominantly used as a support. Next thing to say, because we'll come back to the aluminas themselves in a minute. Next thing to say is look at the various characteristics. The activated alumina has automatically got a lower surface area. Lower surface area means less potential for reaction, so a lower reactivity. The zeolites and the carbon have large surface areas. So if you want to put an active metal on the activated carbon, that's great because it's got a large surface area. The zeolite's got a large surface area, so that's great for that. But of course, that makes them brittle, makes them more sensitive to attrition and mechanical wear and tear. Key things are to look at the pore diameters, and you've already had an exercise in the tutorials around this topic, which was asking you to pick out which was the high surface area and the low surface area so you can tell whether it was reactive or not. So have a look at that tutorial question because it's got a lot of this data in it and it's an interesting question and the answers are now posted up on Blackboard for everything apart from today's tutorial. Right, so what do we know about alumina, which is the top one? So having focused in on the types, we now go up and look at the alumina in a bit more detail. So alumina is susceptible to phase transition, which means that it can change from being a high surface area to a low surface area depending on the temperature that you treat it at. So for those of you in design project that are thinking of using an alumina catalyst, there are very different types. So if it says alpha alumina and one says gamma alumina, I know, but you probably don't, that one has got a very high surface area and the other has got a very low surface area. And the difference between the reactivity of those two things is massive. So if you think you're comparing the same thing, you need to compare the same thing but realize that the alumina and its nature, its state, is very different. And the surface area gives you the idea. So I use gamma alumina predominantly, which is a surface area at the top of the table, which is about 350, 300 to 350 meters squared per gram. But the alpha alumina has only 1 to 5 meters squared per gram. And that's what this would be made with. Okay? Hell of a difference. Now, what I'm hoping is that you've picked up the elements of the course along the way, and that now that begins to tie into things like, okay, I've got a large surface area, I've got large reactivity. I've got a low surface area, I've got low potential reactivity. At the same time, I've got strength versus I've got weakness. So there's always a trade-off on what catalyst you try to use. Other than that, you've got the idea of the pore diameter in nanometers up there. Key thing about the aluminas is as you fire it, things happen to the pore diameter and you lose the smaller pores and you end up with a very big pores. So you're losing surface area, in other words. And the zeolites and the carbon are an order of magnitude or two lower than the activated alumina. So it's important just to pick that up. So if you take this stat, which is the 6 to 40, and compare it with the 0.6 to 2, you get quite a significant difference in the pore sizes. Why is that important? Well, if you've got big molecules, you want big holes. If you've got small molecules, you want small holes. It's as simple as that. So you'd use zeolites where you're talking about molecular sieving, so it's the same size as the molecules, hence its name, it's a molecular sieve, versus something that you can drive a truck through, basically, alumina. So you want something that will react to anything, or give you a little conversion. So, what are zeolites? Apart from being lovely and the mainstay of my career and pay for my holidays every year. Zeolites are silica aluminas. They are, in nature, crystalline. They're made up of silica and alumina, as this young man. Don't play with the end bits that are wobbly, because it will fall off. But you can have a look at it. So what is meant by the black atoms is the black atoms are tetrahedra. Grab a bit that's firm and then handle it with care. Okay? So they're made up of silica and alumina tetrahedra. They end up forming structures, which is a tertiary structure like that, which is beautiful, and porous, but also rigid and fixed in its pore dimensions. So it's known as a molecular sieve, defined by its structure. It has, because of the alumina, an acidic nature. If you don't want to have a look? So the acidic nature comes from the aluminium, which means it also has an ability to ion exchange. Now, I can explain that, and I can do that this afternoon. But for now, let's just keep its key properties. So that aluminium leads you to want to counterbalance that negative charge on the structure with a positive charge. Now up there you've got silica SiO4, because that's a tetrahedra, and it's 4 minus. And you've got AlO4, 5 minus. So they're both negative, so you're going, oh, the whole thing's negative, I don't get it. Well, if you look at the structure, each tetrahedra atom has the spokes coming out, which are oxygens, going to the next atom. But then it goes to another one, and another one, and another one, and they're all interconnected with very little loose edges. When you do that, it means that each bond halves, has half an oxygen. Not a whole oxygen, it's got a half oxygen. So it means that it's SiO2, so you should be writing that down, versus AlO2. AlO2 is negatively charged, SiO2 is neutral. So consequently, the aluminium gives you the charge. Now, there hasn't been one of my PhD students in the last 10 years that actually knew that when asked. Okay? So I'm not necessarily expecting you to remember it, but it's nice, because when you say the acidity comes from the alumina, you're quite rightly going to be confused when you look at it, because they're both negative. So that aluminium O2 negative charge now needs to counterbalance. When it counterbalances, it loves things like sodium. So it's used as an ion exchanger in washing up liquid and powders. So it will ion exchange calcium instead of the sodium, so you can use it to soften water. But you can also use it to pick up strontium and cesium and other things that come out of radioactive effluents. So it's a common, zeolites are commonly used to absorb radionuclides, and young Clint Sharrod and young Dr. Holmes, Stuart Holmes, both do things on ion exchanging of radioactive materials. And they're both in the school, if you didn't know who they were. So that adds to another thing. Zeolites themselves have a unique structure. They're very thermally stable. So people like me make new structures all the time, and we say, we've invented this great structure. My problem is I'm too much like you lot than I am like my brothers and sisters in chemistry. So where these beautiful structures are lovely, and they are lovely, and they're beautifully designed, and it's taken a lot of science, they're not worth a damn because they can't go above a temperature of about 120 degrees C, so they're no use for anything in catalysis, so they're no use for oil and gas. Zeolites will go up to, quite happily, 600, 700, 800 degrees C, and they're still stable. Whereas the stuff that is very nice that's talked about, such as PIMs and MOFs, which you can look up, which are polymeric materials, fall apart when you give them a lick of heat. So they're not so good for catalysis. Brilliant though they are, they're not so good for catalysis. If you want to look up what they are, look on chemistry website and you'll see people working on those. So you got the idea that 25% of the periodic table can be incorporated, so we can ion exchange, we can add to the periodic table, and you've also got the surface area, which is high. You've got a large internal surface area, which is about 90%, so remember the anecdote of the TARDIS, and you've got it. So they open the door and it's big inside. So there's a lot of internal surface, which gives you some kind of selectivity. That one I showed you last week. You handled the red and black model as we were passing it around, and you were quite happily sticking your hands in the middle of it to see the big pore the pore leading into the alpha cage, which was on the inside. So that's A. That goes in washing powder. Why? That's the one that's falling apart in my office, and I didn't dare bring you till I've done some repair on it this afternoon. And it's made of the same units, if you look, those truncated tetrahedra, which are the units here, are present in the one at the top as well. It's joined by the 4 face there, but the 6 face here. That is for me to know and you to just listen to. However, what is important about this baby here is it's got a massive internal chamber, and that chamber causes problems, but it also means it's like a pressure cooker. So it will allow small molecules in, they will react, and they will do something on the inside, which means this catalyst is prone to deactivation, but it just happens to be the major use in FCC, which is fluid catalytic cracking and the production of gasoline. Those 2 zeolites are responsible for, number 1, the biggest bulk use, and number 2, the most expensive. Okay? Now then, prices that used to be, that I used to know, are $2 to $5 per pound of zeolite Y. Okay, so I'll let you convert that into tons, pounds per ton, but you'll come up somewhere, I hope, with a number around 5,000 to 10,000 pounds per ton. So you get the idea, it's not cheap. Okay, spot price for iron the other day was $70 per kilo, I think. Okay, to give you an idea. It might have been $70 per ton, which is pretty expensive, pretty cheap. I have to think about that. You can maybe look that up. But this is important when you're pricing your catalyst for your design projects. Gives you a feel for it. Where do you find information about prices of catalyst? No, you don't knock on Dr. Garforth's door. Lovely though he is, he's never there. Yes, I know that. And he doesn't want to answer the same question over and over again. You go to the Oil and Gas Journal. So you go online and look at the Oil and Gas Journal that's there. You look at anything that says news, Chem-Eng Design News, maybe, but Oil and Gas Journal, just look it up. Every year in January, used to be January anyway, it might be December, they might have changed it, they put in the back the list of prices, spot prices for metals, spot prices for catalysts, how much it costs per ton, etc., etc. We can look in the break, and if I remember, because I've got to sit in on Tom's lecture today, if I remember between, while I'm listening to Tom, I won't go on my iPad and look up the prices and check if the journal's there. Promise, but we'll know by 2 o'clock. All right. So moving on. So that one is the one you're handling. So have a look at the picture and see if you can recognize it. The young lady's holding it. You've got the parcel today. Well done. The music stopped. So that is what you're looking. Yeah, that's it. You can hold it, but they know it, so they can see it, and you can hold it. And you're losing a bit of the left-hand side, right-hand side of it, I think. I knew something would drop off. That's it. Just push it in if it will. If it doesn't go, don't worry about it. It took approximately 6 months for somebody to make that, by the way. That person now works at Saudi Aramco, by the way. His name's Dr. Rayed Abu-Dawood, so bless him. He'll love you if you break it. 6 months of his PhD making that. So that ZSM5 is an additive that goes into the FCC process. Okay? You can see it's different to the ones on the other side, but I'm just showing the beauty of them. I'm not expecting you to draw that in an exam, for example. Okay? But I'm just showing you the beauty of it because you can see the structure. What is highlighted in the grey, to me, is the pentosyl chain that makes up that zeolite. Okay? So they're just different structures, but they're all based on the same elements, silicon, oxygen, and aluminium. Just like we're carbon-based life forms, Mr. Spock. Right. So, mordanite. This is an interesting one because this is a different channel structure. So all those three, A, Y, and ZSM5, are three-dimensional. Mordanite, however, has a different type structure. Notice the terminology written now at the bottom. 12T, 8T, 12T, 8T, 10T. That refers to the tetrahedral atoms on the black, which are the black things in the model, wherever it's got to now. So the black things are the tetrahedral atoms. So when you look at the window, so the two that are studiously looking at it now, look at a window, look at a pore, and you look at the pore, you count the number of steps around the pore, and that equals the number of T atoms. Now, if you were first-year PhD students, that would be really important for you to understand when you're doing zeolites. But since we're a final year class, or we're potentially a final year class, second to final year class, that sort of thing and knowledge of that's really useful to oil and gas people when you go for interviews. They'll be really very impressed that you actually know anything about zeolites whatsoever. My students who are in industry this year are saying, Arthur, that booklet of yours, I've been reading it because I'm working on zeolites. Maria Frogley, who's currently at ExxonMobil, for example. So, although it might not be directly relevant now, it is virtually the mainstay of the oil and gas business, these catalysts, so it's worth you knowing about them and being aware of them. The fact that they've got different structures means they do different things. Hey, didn't know it did that. Right. So somehow the animation's reactivated itself, which is brilliant. So what's the key thing about approximate effective diffusion coefficients? A wonderfully exciting slide. But what it shows you is, remember the pore diameter that we were at before? Typical zeolite A has a pore diameter which is about, according to the text, I think, 3 to 4 angstroms. ZSM5 is about 5 to 5.5 angstroms. Look at the molecules that you've got there. Oxygen and nitrogen are about 3.4, 3.6. Look at the hydrocarbons. Benzene is 5.85. So it's bang on the pore dimensions of the thing that's going around the room. So the holes in that are the same diameter as a benzene ring. So now, when we were talking about before selectivity and things getting clogged and catalysts dying, that's it. That's a really good elevation for me. Thank you for that. So it's really important to understand the kinetic diameter. Now, am I going to ask you to memorize that? No. But I think it's important that you might remember that you can separate oxygen and nitrogen, and you might know that benzene is roughly the pore side of ZSM5, and that makes them molecular sieves, and that makes them shake selective, because that's part of what this course is about. And if the slides work, I have no idea what's going on with these slides today. This is all from last week's catastrophe with the screen. So, having looked at the pore size now, there's a key thing. So what I've got there is I've just put you up a graph to help you understand. When you're looking at selectivity and you're looking at a process and you're trying to pick that catalyst, one of the things that you will see in data is the diameter of a particular molecule against the amount that it uptakes. And the purpose of the pictures is to show you what a molecular model looked like. Now, when you were at school, or sixth form college, or whenever you were doing chemistry, you may have built some ball and stick models, like the one that's passing around that's mine. Or you might have made these things, which are the old ping pong balls at the top. But the purpose of the ping pong balls at the top is to show you the structure of ZSM5, to show you the molecule, which is benzene, that's stuck in it, which shows you that it's that thing there in that structure. And if you look at the diameter of the pore, it's here. Benzene is bigger than the pore. It's almost the same size, but slightly bigger. So what does that mean? You're not chemists, you're engineers. So nothing is to be taken for granted. So when we say the kinetic diameter and the diameter of the pore is this, it's not a hard and fast rule because it's based on theory. It's based on theory that we know exactly what an atom looks like. And we all assume they're ping pong balls because that's what we got taught at school, and we're used to that, and it sticks in our mind. But of course they're not. They're clouds of electrons, and as young old Brian Cox is commonly heard saying on any of his TV programs, it's mostly space. We're mostly empty. What you see in front of us is mostly empty. Preferably not our brains, of course, but mostly we're empty space. So consequently, although it looks like that to us as a visualization, it isn't like that for real. So bigger things can go in, but they have difficulty getting in. And that's the key thing about that graph. Yes, sir?
Two slides ago, you showed different structures.
Uh-huh.
Do they all consist of silicon, oxygen, aluminum?
They do indeed.
So what differs their properties? I mean, what's the difference? Is it their structure, how they're organized?
So you mean, I think your question is really how do they form different structures?
Yeah, and what's the difference between them?
Okay. So if we take this one because it's here, that structure is formed because we, as human beings, direct it. Okay? Zeolite A and zeolite Y can be found naturally occurring, like in that rock I showed you last week. Okay? And they take millions of years to form. But we can make them in the lab in I can show you how to make one, and you can make one, and your grandma can make one in 20 minutes from now. Okay? It's cooking. It's nothing fancy. The ZSM5 is a little bit more difficult because the orientation wants to go to the Y and the A, but it doesn't want to go to that. What's the difference in the properties? The key thing is they will have different amounts of silicon and aluminium in them per unit area. So they'll have unit volume. So they'll have a unit cell which is different. And it means that you'll have different concentrations of acid sites. You'll have different concentrations of availability of aluminium in the structure. I'll pick that up again because it's not an easy question to fully answer. But the key thing is the structures are different because we've made them different. And then they do different things, or we apply them to different processes because they are different structures.
And just one more question.
Yeah.
For the acid sites, it was mentioned in the coursework. You said it was aluminium now. Is it the active site itself?
Yeah, so your aluminium would be in this structure, this would be not the aluminium itself, but the associated hydrogen counterbalancing ion. So, right. As always, your questions are interesting and never easy to solve. So very simple. When you make a zeolite, it's usually this form. Sorry, that's minus, that's plus. You would then ion exchange it to make it that. Then you would simply cook it, and it would make that. So that means that aluminium site, okay, let's assume it's got tails. This is tetrahedra. So let's assume we've got that. Okay, so that would go to that. That means that this one would have an Na plus there, but at the bottom would have a H plus. Okay, so we're just substituting that for ammonia, heating it up, and we get that at the end, and that becomes our product. Okay, and that was on the oxygen, and that would be in the structure. Okay? Hopefully you can read that at a distance. If not, you can take a photo of it. Does that answer your question? Still, he's confused now because he's got chemistry.
I mean, but the atoms go inside that.
So I think your question is, where is the aluminium? So that structure is a chemical structure of one layer. So it's silicon, oxygen, aluminium. Silicon, oxygen, aluminium. So,
That's where the
and it's in,
atoms will-
yeah, now if you've got one there and it's available, it's an active site. Got it? Okay. Somebody tell me why my computer is so slow. So, remember the picture at the top, which was the ball and stick, which is the billiard ball, the ping pong balls. On the other slide, it's just the same slide. So there's no big deal. It's the same slide. But what it's trying to tell you is the channel is a fixed size. The channel, therefore, only lets certain molecules in of a certain type. So, for example, zeolites can be used to separate straight chain alcohols and branch chain alcohols because the branch won't go in. So you can pick the zeolite pore structure to fit the reaction. Do you want me to do that? I can do that. Da, 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 da. Okay, so while you're looking at the slides speak for themselves. But what you need is a little bit of explanation around them. So you can dehydrate N-butanol, but you can't dehydrate isobutanol. Some of you are doing dehydrations of alcohols in your design project, but you're probably dehydrating methanol. So you're trying to drive methanol off to make dimethyl ether that makes olefins. Zeolites do that. ZSM5 is doing that. There are processes using ZSM5 and SAPO34. Some of you are working on that now. This is why I'm doing this course. This is why I put this stuff in on zeolites. The one at the top is just showing you that you can be paraselective. Paraxylene is produced, if you took a disproportionation, start at the beginning, if you take a disproportionation of toluene, that means disproportionation, you lose one and it gives you benzene, and you gain two and you get orthoxylene, metaxylene, and paraxylene, which are the structures inside the zeolite. Trouble is, what that slide doesn't do is it misleads you. Basically, what happens is the structure is limited and the diffusion out is so slow for the two on the left that only paraxylene comes out. And we've looked at that before. So I put that on the board the other week and I gave you a little diagram. But it tells you what's paraxylene used for. It goes into clothes, into terylene. It also goes into PET because you make terephthalic acid, which is COOH on both ends of that little stick. And away you go. So zeolites can be shape selective so that they don't do a reaction, or they prefer to do one type of reaction, or you can use them to be shape selective. So that's the main usage of the zeolites. Now this is a research slide. This is to show you the sort of thing I do, but to say that you understand it at least a little bit. The key thing here is the driving of the reactions, the isomerization versus the rate of disproportionation. So isomerization means we take the molecule in the middle and we make variants of it. So that's a xylene, we make the various para, meta, and ortho. If we go the other way, we make the toluene and we make trimethylbenzene. We make a bigger molecule and a smaller molecule. Hopefully you can see just by the numbers. You've seen the structures. I've not included any zeolites, lots of fancy ones. There's over 220 zeolites, by the way. I've only included the three major ones because even today, after 50 years of research, most people still use the same three types of zeolite. But you can see the difference in the ratios of driving it that way versus driving it this way. Now, importance, because you're going, what's this got to do with this course? Remember right at the very start, we looked at the energy diagram. We saw that when we used the catalyst, we reduced the activation energy and we changed the pathway. And I gave you the question, which one was the best to do a particular process? This is exactly the same example used in industry all the time, and it leads to that very simple diagram we did in the very first lecture that we did. So it all hooks up together. So, main uses, main properties. For example, good questions on this course would be explain what the theory of active sites are. Good questions would be about the theory of the pore model. Another question would be what are zeolites? And another question might be how do catalysts deactivate? Those are the sort of questions I want you to pick up of the last 3 weeks of the course. the other part of the course, we'll do Langmuir-Hinshelwood and talk about models and how you develop kinetics and so on. But that pretty much is what the revision session will cover when we come back just before the exams. So zeolites in catalysis, major use. Acid catalyzed reactions. Why? Because they've got an acidic site. That's the active site. They favor different environments. That's high end. But the key thing is they've got strong sites. They're a polar environment. They're microporous. But because of the acidity and the temperature they'll operate at, they're always prone to coke up. Coke up means coking, deactivation. They don't last that long in FCC. Do you remember how long they last in fluid catalytic cracking? I told you last week. Anybody remember? 15 milliseconds to half of a second type thing. So that's how quickly they deactivate. And that's the thing with the big hole in the middle that I said was like a pressure cooker. You've got a little hole opening up into this big hole, then the molecule gets in, it reacts like bilio on the inside, it oligomerizes and makes lots of other things, and away you go. It's coked up, it's dead. But in the few seconds it lives, it makes all that gasoline, and the oil business has been running on it, and the refineries sorted around it. Ooh, I don't know now. That process has been going since 1923 in different forms, but with zeolites since 1960. So how many years is that? That's a few. That's 54 years by my reckoning, quickly on my feet. Right, so what do we do in the refinery then? It's a lovely diagram, that. Can't remember where I've nicked it from, but it's a lovely diagram. Key thing on it, which shows up beautifully on your handout, the white bits are the bits where zeolites are. But for you as designing processes, it's always very nice to look at. You've got alkylation, you've got isomerization, you've got reforming, fluid catalytic cracking, hydrocracking. Just look at the graph for a minute. It's worth spending a minute on it, just so you can see what you've got. You've got the distilled oil. So here's your crude oil distillation column. The distillation column then has to do various things. You've got the lights at the top, the heavies at the bottom. You have to do things to the heavies. You have to crack them. That means you have to do some residual upgrading. When you've upgraded them, you can get them probably to gas oils, and then you can put them in an FCC unit. That's where the zeolites fit. If you want to hydrocrack them, in other words, take them to produce a stable feed, then hydrocracking is using hydrogen. So cracking is cracking without hydrogen. Hydrocracking is with hydrogen. I love engineers, and in some part chemists as well, because it says what it does on the tin. Okay, so it's hydrogen and cracking. Whoa, don't go away. Come back, come back, come back, come back. So, don't know why the animation's gone completely mad, this. Isomerization is key because you're making more RON. The alkylation, the gas treatment, and the reforming, and the residue cracking don't generally use zeolites, but guess what? So for your information, I've got PhD students working on alkylation, isomerization, hydrotreating, fluid catalytic cracking, and hydrocracking. And I've got 6 PhDs, and that's 5 of them. Okay, so that's what I'm doing upstairs in my labs now. So no matter how old I am, they'll still be doing that in 10 years. It'll get me to retirement. So I won't worry about my life, but I spent my life around those processes. Okay, but that just shows you why I like the slide. Is for you, it's the simplest diagram of a refinery you'll see, but also at the same time, it highlights the bits that are the key parts of the process. Alkylation means joining molecules together to make bigger molecules. Isom means making more isomers so your car drives better. It increases the RON. Reforming means taking things out, breaking molecules up. Distillate hydrotreating is taking out the sulfur. Reforming is taking out the sulfur and the nitrogen. Cracking is what you're familiar with, and hydrocracking is what I've just discussed. So a nice scheme. So, should be in the notes. Now then, when I said, and you wrote it down, check the Oil and Gas Journal, those are prices of dollars per ton from 1988. Okay? Not current day. But if you're struggling and you're doing design projects and you're running out of time and you haven't been able to find a price because the company won't tell you, and the reason the company won't tell you is because you're not going to buy any, and every year they get 1,000 chemical engineering students in the UK asking for the price of catalysts, and they go, it's design project time again. And they just ignore you, generally. So if you're lucky, you can find out because you've got mates who are working in the various companies that might be in the 4th year, 5th year. In effect, they've graduated last year, and you'll be able to price. But it gives you a scale of how much price per ton. Zeolite's Forgesite works out to be about $1.5 to $3,000 a ton used in cracking, and I estimated it was about 5 to 10K now. So check the current prices, but you've got a reference point. Okay. What else do I want to say? So an exam question in the past might be, name me a few zeolites and tell me what processes they're involved in. It doesn't say what price they are because it links to the refinery process before. Okay. So that's your famous FCC unit for those of you who drive past refineries and want to look for it. The thing that you most often recognize is the regenerator, because it's usually a big chunky thing and it looks pretty much like that. It looks like a massive hopper. But you can see what the process looks like. You've got the riser where the catalyst goes in with the feed. Feed comes along. So it says fresh crude oil there, but it's usually gas oil that comes in. Gas oil, up the riser cracker with the catalyst, and out come the products. And you can see what the products are there. Note, the reactor where it says reactor is not really the reactor. It's the thing at the top that's got a couple of cyclones on it to take out any dust, and it also allows the catalyst to fall back so it goes down the regeneration loop. So let's just trace the catalyst for you. Catalyst comes in, pneumatic conveyance in along with the cat oil. It goes all the way up. It settles, it loses its acceleration, and it falls back. The fines are separated here by cyclones, and they're taken out. And why are there fines? Because this is a fluidized process. Why are there fines? Because it's a fluidized process and the thing grinds against itself. So it wears itself out. And it's 25 to 40% of the catalyst is replaced annually. So you lose 25% to 40% of your catalyst every year. When it's £3,000 a ton, and it might now be £10,000 a ton, that's quite a lot of catalyst that just disappears. But do be aware that attrition is a major source of problem in this process. So now you're in the thing, it drops out, it falls down the sides, and it goes into the regenerator, where it's steam regenerated. So remember we said coking was a form of deactivation. So in that section there, you're using steam. You can see that you've got air and steam to help protect the catalyst at a high temperature. So your process in your riser is 480, and the temperature I've seen is up to 535 degrees C, but that's a good enough range. But your regenerator is operating 200 to 300 degrees hotter. 250 degrees hotter. So your zeolite's got to stand that temperature. Most catalysts don't stand those temperatures. So this whole process used to be done with sand, fluidized sand. It started with sand, it moved to sand with something on it. It tried to move, it went to clay, then moved to zeolites. Okay? And that's it. That's 100 years of development. Engineers. Humbling for a chemist who tries to make new catalysts all the time. All right? So in 100 years, you've used 3 catalysts. In 60 years or 70 years, you haven't changed the thing the way it looks. There is a tie-up now with Saudi Arabia and Japan, which is actually using a downer rather than a riser, so the catalyst is falling down, and there's about to be a pilot plant built in Japan around a new style. It's taken them that long to come up with a new innovation on the process, and they've got a lot of problems with it. But it's going to go to pilot. Last bit, that's what it looks like. So you can have a look at what it looks like. So you can see the reactor itself was actually the top of the reactor that you're really looking at. You've got a column at the back, your risers in here, down here, your regenerators over there. You usually can see that typical arrangement. This is known as a J-bend. Obviously, looks like a J. Ladies, you remember I told you the anecdotal, and you two will be prime candidates. Go in with a jackhammer. I wasn't kidding. You'd be going in there, because no guys can get in there with all the gear on it. It needs small, diminutive people to go in there. And it's usually ladies that get sent in. And that's Chevron Texaco anecdotal story from about 15 years ago. I have no way of proving them untrue. I have no way of proving it true. But that was told to me on a little consulting project I did a long time ago. So What's inside there is something called a refractory tile, and it's basically very resistant to anything. I used to have one in my lab a long, long time ago, and it was heavier than a cement tile. But if you imagine a double thick cement paving stone, knock it down into a half that size, triple it in thickness, quadruple it in weight, that's what the ladies go in to drill out with a pneumatic drill. Not very pleasant job. Wouldn't be volunteering to do that on shutdown if I was you. I've run out of time, so I'll stop. But one of the things that's anecdotally true is that 5 years ago, Rachel Perry, who's at ExxonMobil, I think, was there on placement when they had a shutdown. I think I've had another student on placement in... where's the refinery in Wales? South Wales. Is that Texaco? Texaco Chevron. They shut down about 3 years ago, and the student on placement loved it because they went in every single reactor and had a look around, but worried themselves to death because nothing was working. So they couldn't do anything on any big kit, but they still got to see the inside of the reactors. Anyway, that's as close as you'll come, and I'll come to touching it and working on it, maybe. Maybe you'll actually get to work on it. I'll let Tom come in. Come in, Tom. I'll escape there, just so I know where I'm up to. Thank you very much for your attention. I'll see you at 2 o'clock. Everything worked okay, but my animation's gone completely mad on the... I'll switch that off now. That's a lecture that needs animation, so if the voice works on my lecture, that'd be perfect. So, but this thing, it's got animation that is now. So it's like, what happened? I copied the slide, took the animation out, now it's reinvented the animation again. So it was putting the bottom of the slide on, then the top of the slide. I'm like, what the hell it was doing? Is that a mind of its own?
Did they
I didn't
visualize
I didn't get that. I'm going to do that. No, I didn't do it. I'm going to do it this week because the structure's here for my CLI.